Okay, so let's talk about another example, the one that I think is kind of interesting right here. It says that, okay, let's say we've got the rate of change of p is proportional to p. When t is equal to 0, p is equal to 5,000. And when t is equal to 1, p is equal to 4,750. So we ask, what is the value of p when t equals 5? Well, we now consider this sort of an initial condition kind of problem because not only are we told about a relationship for the rate of change of p with respect to time, so that's our rate of change of p, and it's proportional to itself, but we're also given two conditions in which we might be able to figure out what particular function will produce this result where t is equal to 0, p is 5,000, and when t is equal to 1, p is 4,750. All right, well, let's set it up. First of all, this statement, the rate of change of p is proportional to p, means that we've got some sort of equation kind of like this one. The derivative of p with respect to t is proportional to itself. So there's some constant times p that makes this true. All right, so if this is the case, and we're given this equation, what we're going to do is we're going to use the separation of variables. That means that we're going to gather all of our p terms to one side, so the derivative of p divided by p is going to equal to a constant times the derivative of t. All right, so what do? Well, we're going to integrate on both sides like we've been doing. So the integral of dp divided by p is going to equal to the integral of k times dt. And using our super integral powers here, we know that now we're going to get the natural log of p is equal to k times t plus a constant. One of the assumptions that we're making right here, by the way, we're starting with t is equal to 0. If this is with respect to time, then we're going to assume that t is greater than 0, greater than or equal to 0 as far as our time goes. And so that might mean that, well, p is also going to be positive. So I don't need to write this as the natural log of absolute value of p as we've been doing. So in this case, we're going to assume that if p is greater than 0, then we're in the clear right here. We're going to get some positive answer. Uh, so we just write it as the natural log of p. All right, what does that mean to us? Well, that means that p itself, which is what we want to solve for, is going to equal to e raised to the k times t plus the constant. Now a little bit of rewriting gives us this. P is equal to e to the k times t power, k times t, times e to the c. But we're going to treat this as a constant right here. So rather than having to figure out what that small c is with e as its base, it's a lot easier to handle it just as its own little constant right here. C times e to the k times t. And that's what we're going to go with as our model. All right, so how do we do this? Well, remember we're told that when t is equal to 0, p is 5,000. So that means that 5,000 is going to equal to c times e to the k times 0. Well, any base raised to the 0 power other than 0 is going to equal 1. So in other words, 5,000 is equal to c. That's called an initial condition, and that always gives us that starting constant. So now we've got this model that p is equal to 5,000 times e to the k times t. Now you notice we still have this other constant k sitting around. And so we think, well, what do I do with that? Well, that's why we're given a second condition. And in these kind of problems, you typically have to have at least two conditions to be able to solve this. And we're told that when t is equal to 1, p is equal to 4,750. So 4,750 will equal 5,000 times e to the k times 1. Well, that's just e to the k. Well, a little bit of algebra magic right here. shows that if we were to go through and divide 4,750 by 5,000, we're going to get e to the k. And so if we want to solve for k, we're going to take the natural log of that quantity, 4,750 divided by 5,000. So I put this into my magic little calculator right here, and I come up with a quantity, and I'm just going to round, 0.0513. Now I will caution you to be very careful when rounding digits, right? Because we are dealing with exponential functions with bases. Very small errors can lead to very big errors in later calculations. So be careful that if you're going to do this, you round to enough digits. This is enough digits for our example, but be careful to read through the examples. I would usually carry around at least 4 or more decimal places if you have 100th decimal as your goal. All right. So what does our model now say? Well, now we know that P is going to equal to 5,000, which was C, times e to the negative 0.0513 times time t. And of course the question was, well, what happens at t equals 5? Well, if we substitute in at t equals 5, well, now it's just a straightforward substitution. And I put that into my calculator, and I found that P was equal to 3,868.9. Now, you should put this into your own calculator and verify that that is in fact the case, but that's what we were after, and so now we're done with that example.